Good evening all of you. Now we are going to see about the applications of a differential equation. We know that differential equation means the rate of change in the given system. This concept is mainly used in science, engineering and medical chemical reactions, population dynamics, organism growth and the spread of diseases. So, the differential equations are absolutely fundamental to modern science and engineering. So, this concept is the most common use of differential equation in science is to model dynamical system. So, first we know that what is dynamical system. That is a system that change in time according to the some fixed rule. So, now we have usually we write differential equation the dependent and independent variable, that is y is dependent and x is independent, means we can write the rate of change in the given system is dy by dx, that is here y is depending on x. Here in instead of dynamical system, here we have used the independent variable x as t. So, we have the differential equation like this, dy by dt equal to dy by dt equal to d cube into y squared, instead of the ordinary differential equation in terms of x and y dash equal to x cube into y squared. In addition, in this section we are going to see about the applications of differential equation in physics and chemistry. First, exponential growth and decay. So already we have discussed in class differential equation is mostly used in plant growth in terms of the time variable t. So here the time t is a independent variable. So here for exponential growth and decay concept, first we introduce the natural growth equation in terms of differential equation. So first consider the natural growth equation is dy by dt equal to k into y. Here the given system is y in terms of the time variable t. So we can write the rate of change as dy by dt. So y is the system, it depends on the independent variable t. So we can write dy by dt equal to k into y, where k is a constant. Then now we solve the above equation. So for that we integrate it, where the above equation we have the solution like this, y equal to y naught into e power kt. Here where y naught equal to y of 0, this y naught is the initial value of t, initial value of y. The constant k is called the rate constant or growth constant. So we can say the constant k is the main role in the growth and decay. So we can say the k is a rate constant or growth constant. The sign of k governs the behavior of the solutions. So there are two cases here. First case is if k greater than 0 and the second case is k less than 0. First, the constant k greater than 0, that is a positive number, then the value of y increases exponentially over time. This is called the exponential growth. And second case, if k less than 0, then the variable y decreases over time, approaching 0 asymptotically. This is called an exponential decay. So here we have two cases in terms of the sign of the constant k. First one is k greater than 0 and second one is k less than 0. And we can see the figure. First case k greater than 0, we can see that the value of y equal to e power kt increasing exponentially into over time t. In the second case, k less than 0, we have y values decreasing over time. So if the value increases, that is the y increases exponentially over time in terms of the positive value positive constant k, then we can say that exponential growth. Suppose k less than 0, we have a exponential decay. So one more case we have considered. Suppose in the figure 1 we have y equal to e power kt. In these two cases, in the case we have in this case where k is a negative number, suppose this k is negative, the natural growth equation can also be written as dy by dt equal to minus r into y. But what is the natural growth equation? Dy by dt equal to ky. Here we have write, instead of k, we can write minus r, where this r equal to modulus of k. So this modulus of k must be a positive number. So r is positive, but here we have take that k value is negative, so we can put the sign negative minus r into y. So the above equation, we have solved the above equation, that is we integrate the above equation dy by dt equal to minus r into y. We have the solution y equal to y naught into e power minus rt. Then following example illustrate several instance in science where exponential growth and decay is relevant. Consider a colony of bacteria in a resource rich environment. Here resource rich means for example that there is a plenty of food as well as space for the colony to grow. In such environment, the population P of the colony will grow as individual bacteria reproduce via binary fission. Assuming that no bacteria die, so the rate at which such a population grows will be proportional to the number of bacteria. So usually we write dy by dt equal to k into y. Here we consider that y, that function ys, here we consider that y is the population p. So we can write the differential equation in this type, that is dp by dt equal to k into p. That is, now we are seeing about the growth, so this k value greater than 0. So the first to formulate the differential equation, that is the growth equation, dp by dt equal to k into p. That is, here k is a constant of proportionality. Then for example, suppose here we consider the value of k is greater than 0. So we can take the value of k equal to 3 per hour. It means that the individual bacteria cell has an average of 3 offspring per hour. Then we go for example 2. Then consider a sample of certain radioactive isotope. Here we are going to take the value k is negative. So we have the differential equation dm by dt equal to minus r into m in the special case. So if we take the value of k is negative, we can write dy by dt equal to minus r into y. So here we take y as the mass m. So dm by dt equal to minus r into m. If we integrate, we have the value, the solution m equal to m naught into e power minus r t, where this m naught is the mass of the sample at a time t equal to 0. Here we have the figure exponential decay of a radioactive isotope and the exponential growth of a bacteria population. That is a k greater than 0 case, and k has a negative value. Then next we go for what about the half-life and doubling time. So doubling time of a system. So first, half-life. What is half-life? The rate of exponential decay is the half-life given a decaying variable y equal to y naught into e power minus rt, where r greater than 0, because r equal to modulus of k, that is a positive number. So here we have here we have consider y naught as half, so y equal to y naught by 2, where this y naught is an initial state, y equal to 0. So y equal to half-life we are going to study. So y equal to, we can take it as y equal to y naught by 2. So we substitute y equal to y naught by 2 in the above equation. We have the equation like this. Similarly, if we solve the following equation, we have the solution for t. Similarly, given a growing variable y equal to y naught into e power kt, where k greater than 0, we can measure the rate of exponential growth using the doubling time. So here now we in this type we consider y equal to 2 times initial state, that is y equal to 2 into y naught, because here now we are going to study about the doubling time. So the state y equal to 2 times the initial state. In the previous case we have discussed about the half-life. So we consider y equal to y naught by 2, but here we are going to study about the next we go for a differential equation, application of differential equation in physics. Here we consider a simple electric circuit, that is RC circuit. There are two components. Here we consider two components. The first one is a resistor and the second one is a capacitor. So first we know that what is resistor. A resistor is an any circuit component such as a light bulb that resists the flow of electric charge. So this resistor obeys Ohm's law. So V equal to IR, where V is a voltage applied to the resistor and I is the rate at which the charge flows through the resistor, and R is a constant. Then this is called the resistance. Then what is a capacitor? A capacitor is a circuit component that stores a supply of electric charge. When it is attached to a resistor, the capacitor will push this charge through the resistor, creating electric current. So capacitor obey the equation V equal to Q by C, where Q is the charge stored in a capacitor and C is a constant, is called the capacitance of the capacitor, and V is a resulting voltage. Then now we are going to connect these two concepts in terms of a differential equation, because here we are using the term I. I is the rate. So rate of change, the rate at which charge flows the through the resistor. So here the rate of change is happening. So we can use the differential equation dy by dx. So in RC circuit, the voltage produced by a capacitor is applied directly across a resistor, setting the two formulas for V equal to each other gives. So we can write I as first we equate these two equations, first and second equation, resistance and capacitor equation. We have IR equal to Q by C, but we can substitute the value of I as minus dq by dt, because the rate I at which the charge flows through the resistor is the same as the rate at which charge flows out of the capacitor. So out of the capacitor, so we can put the negative sign. Then substitute the value of I in the above equation. We have the given equation, dq by dt equal to minus 1 by RC into Q. It flows that the amount of charge held in a capacitor will decay exponentially over the time. Q equal to Q naught into e power minus RT, where R equal to 1 by RC. So in the case where the resistor is a light bulb, this means that the bulb will become dimmer and dimmer over time, although it will never quite go out. Then the next concept is a separation of variable. Then the further we are going to see about the Newton's law of cooling. It is also an physics term. For that we are using the concept separation of, for solving the Newton's law of cooling, we are using the concept separation of variables. So first we know what is Newton's law of cooling. The rate at which the temperature of a body decreases is proportional to the difference of temperature between the body and its environment. In symbols we can write dt by t equal to minus k into t minus te, where this capital T is a temperature and Te is the temperature of a environment, and K is a constant proportionality. We can solve this differential equation using the separation of variable. That is, the above equation we have to integrate. For that directly we cannot integrate. First we have to separate the variables, then we integrate. Then solving for t, integration, after the integration we get the solution as t equal to te plus c into e power minus kt, where the value of c changed. This function decreases exponentially but approaches environment temperature Te as t tends to infinity instead of 0. Here in figure it is a cooling of warm body. This is an Newton's law of cooling. Then example 5 is an CheMistry concept, that is how the differential equation applied in the CheMistry concept. The rate, here we consider the system as system Y as a chemical term, nitrogen dioxide. So here we are going to decompose the nitrogen dioxide. I think you have an idea about the composition and decomposition. In general, composition means if f and g are two function, if we are going to composite these two functions f and g, we have with a variable x, we can write f composition g of x as f of g of x. That is, we are composite the f and g in a single term, but in terms of decomposition we separate the composition of f and g in separately decompose the into two terms, f and g. That is a separation of variables. Here we consider the nitrogen dioxide. So 2 NO2 we decompose into 2 NO plus O2. Here we have two molecules of NO2. Here we can the rate of change occur in this reaction. So we can write in terms of differential equation dy by dt, that is here y equal to NO2, nitrogen dioxide. So d NO2 by dt equal to minus k into NOT the whole square, because the rate at which the reaction occurs is proportional to the square of the concentration of NO2, that is 2NO. So minus k, here we are decomposing, so minus k into NO2 the whole square. This NO2 is the concentration of NO2 and k is a constant. We can solve the equation using the separation of variable. First, in general, first we write the given system in terms of differential equation, then we integrate, then we get the solution. First, for that we now we are going to integrate the above equation, then separate the variables. We can solve the this equation using separation of variables. First separate the variables, then integrate, we have the solution. Example 6, here I have given the one more example, example 6. Also then just go through the example 6, then we go for example 7. It is a real life problem we are going to solve. Here an apple pie with an initial temperature of 170 degrees Celsius is removed from the oven and left to cool in a room with an air temperature of 20 degrees Celsius. Given that the temperature of pi initially decreases at a rate of 3 degrees Celsius per minute, our aim is to find how long will it take for the pi to cool to a temperature of 30 degree Celsius. Here they have given what is that is the temperature cooling. So we can use the Newton's law of cooling, example 4. So first we have to construct the differential equation. So dt by dt equal to minus k into t minus T, that is Newton's law of cooling formula. Then here we have the environment temperature TE as the room temperature 20 degrees Celsius. So here we substitute dt by dt equal to minus k into t minus 20. The initial state, that is T of 0, is 170 degrees Celsius. The initial temperature is 170 degrees Celsius. Then the rate of change in T, then T dash of 0 is 3 degrees Celsius. That is the temperature of the pi initially decreases at a rate of 3 degrees Celsius, that is T dash of 0. That is the rate of change in T is T dash. Why we put here a negative symbol is the temperature is decreasing, so here we have the negative symbol minus 3, where this T is the temperature of pi in Celsius, then T is the time in minutes, and K is an unknown constant. We can easily find the value of K by plugging the information we know about T equal to 0 directly into the differential equation. For that, then we have the solution of K. Then the above examples are the examples of first order differential equation. Here we have the next concept is here we have the second order differential equation. dy by dx is a first order differential equation, then d squared y by d squared y by dx squared is a second order differential equation, that is y double dash. Here I have given the second order differential equation concept here, and then also I have given some more examples. Suppose it follows that suppose k equal to 0.20, we find the value from the above example. Now the general solution to the differential equation is t equal to 20 plus c into e power minus kt. If t equal to 0, then we have c equal to 150 degree. Substitute this c value in the above equation. We have t equal to 20 plus 150 into e power minus 0.02 into t. So our aim is to find the how long it will take for the temperature of reach 30 degrees Celsius. We plug in 30, 40 and solve it. We get the time t is 135 minutes. Here I have given the exercises. Then finally I have given the answers for your reference. Just go through all the problems. Then one more example of Newton's law of cooling in crime investigation. Here the detective came at 10:23 a.m. and the temperature of body is temperature of body is 26.7 degrees Celsius and temperature of room is 20 degrees Celsius. After an hour, temperature of body is 20.8 degrees Celsius. Assume that the body temperature was normal, that is 37 degrees Celsius. Then we have to find what is time of death. Let T equal to TE, environment temperature TE plus T naught, initial temperature T naught minus TE into e power minus KT. It is a Newton's law of cooling. Then let the time of death be capital X. Then we are going to find the value of X before the arrival of detective. Substitute given values in equation 2. We have T of X and T of X plus 1. Solving these two equations, we have the two equations. Then taking log on both sides of the above two equations, we have the equation 3 and 4. Then divide equation 3 by 4 we get the value of x, that is x equal to 7 hour. Then this is the murder took place 7 hour before arrival of detective, that is 3 o'clock 23 minutes. Thank you.